An abstract data type, ADT, represents a high-level, conceptual model of a data structure that specifies the type of data stored, the operations that can be performed on the data, and the behavior of those operations, without exposing the underlying implementation details. ADTs promote abstraction by separating the what from the how, enabling programmers to focus on logical design rather than internal mechanics. Every ADT supports a set of fundamental operations that define how users interact with the stored data. One of the primary operations is creation or initialization, which prepares the ADT for use by allocating memory, defining capacity if required, and setting initial control variables such as head pointers or size counters. Once created, the ADT becomes capable of holding elements. The next crucial operation is insertion, which refers to adding new data elements to the structure. Depending on the ADT type, insertion may occur at the beginning, at the end, at a specified index, or based on a priority condition, such as in priority queues. Insertion must maintain structural consistency, update size indicators, and ensure that the ADT remains valid after the operation. Complementing insertion is the deletion operation, which removes an element from the ADT. Deletion can target the first element, last element, a specific element by value, or an indexed position. ADTs must carefully handle deletions to avoid memory leaks, dangling pointers, or inconsistent links, especially in pointer-based structures like linked lists, trees, and graphs. Another fundamental operation is searching, which aims to locate a specific element based on a key, value, or index. Searching may involve linear scanning in unsorted lists or efficient logarithmic time searching in sorted structures like binary search trees. Search operations help retrieve useful information or validate membership within the ADT. After locating an element, the ADT may perform an update or modification operation, which changes the content of an existing element without altering the structure itself. Updating is essential in applications that require modifications to stored information such as editing student records, modifying weights in graphs, or changing priorities in scheduling systems. Another important operation is traversal, which involves visiting each element of the ADT in a defined order. Traversal allows users to process data sequentially, display element values, generate reports, or apply algorithms like sorting and searching. Each ADT defines traversal rules appropriate to its structure. Arrays follow linear traversal, linked lists follow pointer-based movement, and trees use pre-order, in-order, or post-order traversals. Traversal is also used in complex operations such as copying, merging, or comparing ADTs. Many ADTs support sorting as an essential operation, which involves rearranging elements in ascending or descending order. Sorting is crucial for optimization, reducing search time, and ensuring meaningful organization of information. Sorting may require special algorithms like bubble sort, merge sort, or quicksort depending on the complexity and structure of the ADT. Some ADTs also support merging, which combines two ADTs of the same type into a single, unified structure. For example, merging two sorted arrays or linked lists creates a larger sorted list, while merging graphs forms bigger networks. Merging must preserve structural integrity and ensure appropriate ordering. Several auxiliary operations also support the efficient usage of ADTs. These include checking whether the ADT is empty, which prevents invalid operations like deleting from an empty stack, or checking whether the ADT is full, which is applicable to static structures like arrays and fixed-size queues. Other utility operations include retrieving the size or capacity of the ADT, clearing all elements, or comparing two ADTs to check equality. In specialized ADTs, operations expand beyond the basic set. For instance, stack ADT supports push, pop, peek, and is empty operations. Queue ADT supports in-queue, dequeue, front, and rear. Tree ADT supports insert, delete, search, and various traversals. Graph ADT supports add vertex, add edge, remove edge, and path detection. These specialized operations arise from the nature and intended usage of the ADT. The power of ADTs lies not just in the operations they support but in the abstraction they enforce. A user performing an insert on a list ADT does not need to know whether the list is implemented using arrays or linked nodes. The behavior of the operation remains consistent. This abstraction enhances modularity, allowing implementation changes without affecting the rest of the program. ADT operations also support error handling, such as guarding against invalid indices, memory overflow, or attempting to delete non-existing elements. In software engineering, ADT operations play a crucial role in defining software modules, interfaces, and APIs. They enable developers to build robust, reusable code by clearly specifying what actions an ADT must support. The operations form a contract between the ADT and the programmer, guaranteeing predictable and consistent behavior. Furthermore, ADT operations simplify algorithm design because algorithms can interact with data structures at a conceptual level rather than dealing with complex internal details. This not only reduces development time but also improves program clarity and maintainability. In summary, the operations of an abstract data type form the core mechanism through which data is accessed, manipulated, and maintained in any software system. They include essential functions such as creation, insertion, deletion, searching, updating, and traversal, as well as advanced operations like sorting, merging, and utility checks. These operations define the behavior of the ADT and ensure that it meets the requirements of abstraction, modularity, efficiency, and reliability. By understanding and implementing ADT operations effectively, programmers gain a powerful tool for designing scalable, structured, and efficient software systems across various domains such as databases, operating systems, networking, and embedded systems.